All right, welcome to part 2 of our experimental design lesson. And we're going to talk about a few more terms today. So we're going to start out with placebo. We didn't really cover that in the last video. Now what placebo is a fake treatment. Chances are you've heard of this, that it's used a lot, especially in drug trials. They'll give someone like in a case of like to treat anxiety, they'll give one group of people their super medication, and then they'll give someone else like a sugar pill, and then they see how the results compare, because sometimes psychologically people will feel a difference, or maybe just the hope of difference or hope of change is enough to kind of make the body produce change. So that's something you want to be aware of, the placebo effect. What I did was I created a very rudimentary experiment down here. I did not account for any confounding variables, but started out with 50 volunteers and randomly assigned them to either a hair tonic or water. And I'm going to add in balding volunteers here. As many of you know, I do not have much hair, so this would be me. All right, you volunteer, random assignment. So you can either get the hair tonic or the water. Now here's the thing. You might want to, maybe you tell them, or maybe you don't. That's an option. That's where you get into the whole concept of blinding. Now a single blind experiment, that's when the subject doesn't know, but those implementing do. So in this case, that would be, you give each person like a bottle and say, okay, try this, measure their hair growth, and then compare. And then you see if there's an actual difference. So that means maybe the people who are receiving the hair tonic and the water, they don't know which one they're getting. They don't know if they're actually getting this new hair tonic or the water. And the reason for that is because sometimes psychologically, if people know they're getting a treatment, they're more inclined to think that there's a difference, or who knows, maybe even the body can produce a difference. So single blinding is when the subject doesn't know, but those implementing do, meaning at the very beginning here, the scientist who's giving it to them knows who's getting the hair tonic, knows who's getting the water. So when they're measuring, they know which subjects got which. That's single blinding. Now for double blinding, that's when neither the subject nor the person implementing the experiment knows who got the real treatment. So what that would mean is that maybe the scientist at the beginning, mixes up the bottles or whatever. He has no idea which one is going to whom, measures the hair growth, and then compares. The reason they do double blinding sometimes is so that the scientist or whoever's implementing the experiment doesn't impose any sort of, that's what I'm looking for here. They don't want to impose any sort of change. Sometimes they're so hopeful for it that maybe they impose it, or maybe there's some sort of favoritism towards one treatment or the other. So that's why you have double blinding here. And again, that's when the subject doesn't know, and that's when the person implementing the experiment doesn't know. So again, this was a very rudimentary block design. One thing you want to notice though, I did include random assignment here. That's always important. You always want random built in the statistics. Random's always good. You want random to be involved. So in this case, it's random assignment. We randomly assign half the people to get hair tonic, half of them to get water, measure hair growth, and compare. So again, single blind would be if those receiving the hair tonic had no idea, but the person giving it did, knew who got what. Double blind would be if the people who got the hair tonic had no idea what they were getting, and the person giving it to them and measuring their hair growth had no idea what they were getting. Now, ultimately, there's someone overseeing the experiments to compare the results, so they know what's going on. But the people who are directly interacting with those involved in the treatment, they don't know what's going on, and neither do the subjects. All right, now down here, you'll notice I put together a block design, and figure I'd go through this a little bit to give you an idea what block design looks like, and it'll give us an opportunity to talk about a few other terms. What I did here was I started out with 50 10th grade students. I separated them by males and females. Why? Because what we're testing here is we're going to have students either do a remote model or do an in-person model, take the PSATs, and then we're going to compare the results. By blocking them by males and females, what I'm doing is I'm accounting for a confounding variable here. Maybe gender has something to do with this. We don't know. So what I'm doing is I'm separating by gender, so that way that can't come into question when I'm looking at my results. So say for some reason I noticed that the remote students did better than the in-person students, then I know it's going to have nothing to do with gender specifically. Now, of course, you can always take it a few steps further with confounding variables. You can think of other things that might affect it, like, let's see, maybe access to technology, maybe how well a student did before they were assigned to remote learning, or whether they were assigned to an in-person model. Those are confounding variables you could account for. We didn't here. Kept it kind of basic. So we separated the males and females, then using random assignment, assigned half of them to remote, half of them to in-person. Had them take the PSATs, then we compared the results exclusively by, first we did it by males, and then for the females did the same thing, randomly assigned them to remote and in-person, had them take the PSATs and compare the results. And then what you would do is compare the results from each of those specific groups that you split it up into. Maybe you notice that, when I separated by males, I noticed that the males remotely didn't do as well as those who had the in-person instruction. However, when I did it by female here, I noticed that the females did better when they had the remote instruction as opposed to in-person. Then I could say, I could come out with the conclusion that based on the treatment I imposed and based on the variables I accounted for, I noticed that females tended to do better with remote learning and did better on the SATs, whereas with males, it was the other way around. Of course, bear in mind, I'm just making this stuff up. But this is just for the sake of constructing a situation to give you some perspective. So again, you can always account for more confounding variables. And again, they'll make your block design get a little bit deeper. All right, so what else I mentioned here was called a matched pairs design. Matched pairs are very common. It's a method where pairs are matched up by similarities, or individuals are given two treatments in random order, and then the results are compared. What that could look like in our case up here, right? When I separated the males, and I separated them in half, right? Half of them getting remote, half of them getting in person. Maybe what I would do is I would pair up remote and in-person males here to compare their SAT scores. How could I pair them? I could do it by a lot of things. Maybe I'm going to match them up by birthday. Maybe I'm going to match them up by GPA. Maybe I'm going to match them up by neighborhood. There are a lot of different options here. But when you're doing matched pairs, if you're using two different individuals, you can match them up by some sort of similarities. It's common often, sometimes they'll do it with brothers and sisters or even twins. They'll take twins and then they'll compare results with twins. You notice you can do the same thing here with the females as well. Do a matched pairs design. Again, pair them up by some sort of similar characteristics, compare the results, and then compile the differences. Which, believe it or not, I did down here. Now, I made a nice little dot plot, and it's very, very rudimentary, bear in mind. Now, say we did this, right? We took all the differences and we plotted them here. Male, female, you'll notice I did not differentiate with my dots. But what I did was I took my matched pairs, I took the respective in-person score and subtracted the remote score, and I applied that difference here. You'll notice in this case, there were a lot of dots clustered around that 0. As a matter of fact, I did not place any much further than that. If I am looking at this, right, if I'm analyzing these results, I'm noticing, I'm not noticing much of a difference here. Some had higher, some had lower, based on my pairs. I could come to the conclusion that there's really no difference based on what I'm seeing here. Because if there was a difference, I really shouldn't be seeing all these differences of 0. However, if I saw something like this, right? If I took the difference in scores, and I took those matched pairs that I did, right? Those similar people, matched up their scores. And then I looked, negative 300. I see a lot around here, a lot around here. And then the closer I get to 0, the more it kind of disperses. I'm seeing a lot less values here. Now, if there really was no difference, I'd expect to see a lot of values right here around 0. But I'm not. I'm seeing a lot right here in that negative 300 range. And that's what's called statistically significant. When you're seeing a lot of results that you don't expect. Now, frankly, if you just saw a few of them up here, I would not really pay too much mind to that. Like, you might see a few scattered here and there. That's not really a big deal in the grand scheme of things when you have this many scores really clustered in the center. You'd expect to see a few spread out. That's not a big deal. That's not what I would call statistically significant. However, when you get down here and you're expecting to see like little to no difference, and you notice quite the opposite, then you can jump to that statistically significant term and say, I know there's a statistically significant difference here between those who did it in person and remote. And in this case, we're getting negative scores, right? That would have to mean that these scores, whoops, that did not look good at all. Let me try that again. There you go. I noticed that the remote scores were higher, right? Because if I'm taking a lesser value and subtracting a higher value, I'm going to get negative values. So I'd see a statistically significant difference here, and I could come to a conclusion based on what I'm seeing that maybe remote models are more effective when getting ready for the SATs than in person. Again, I'm just making this up. I'm just using this for the sake of having data to look at. But I think you guys are getting the idea here. The goal is that if you're plotting these differences based on the matched pairs, and you're noticing a lot of things that you don't expect to see, that's statistically significant. Of course, later in the year, you're going to learn how you can actually take the percent of data you're seeing against what you expect to see, and you can actually come up with some pretty concrete results. Right now, we're just kind of dealing in vague terms here. Just based on what we see, we could say that's statistically significant. All right, so last thing I want to do is I want to kind of break down vocabulary, because this is a really common mistake a lot of students make when they take statistics. You're learning all sorts of new vocabulary about, you get sampling and you got experiments. And people tend to interchange the vocabulary, and that is a really common mistake you do not want to do. It's an area where you can lose a lot of points for one thing. And also in a statistics course, I hate to say it's flat out wrong, but it kind of is. So here are the things you want to think about, right? First of all, in sampling, we tend to have strata when we make groups, right? Those are our groups when we're sampling. You do not have strata, or you don't do stratifying within an experiment. That's what's called blocking, right? That's when you group in experiments. That's blocking, when you account for those variables, right? Now, in sampling, you can have bias, right? That's when you under or overestimate a value within the context of what you're looking at, right? And with the context of your population. However, you do not have bias in experiments. You do not have that. You can have confounding variables, right? Or you can even throw in factors. That's another term you can use. These are all things that can affect your results in the terms of an experiment, right? Give you results that might mislead you. That would be confounding variables. However, when you're dealing with sampling, you're going to have bias here. So these are things you want to watch out for. Now, in sampling, you have random samples, right? We like doing that. We like things to be random. I'm going to use a random number generator and generate a random sample. You do not have that in experiments. You have random assignment. Again, these terms, they have similar definitions, just different contexts. And these are terms that get thrown around a lot. Unfortunately, I've seen students lose a lot of points over the years by doing this, not just in my statistics courses, but in others. So you do not want to fall into this trap. It's always good to have this somewhere, so you know that when you're using these terms, like when you're describing your results, maybe if you're describing the results of a sample, right? That you're not going to use these terms from an experiment. You're not going to talk about blocking in a sample. You're not going to talk about confounding variables in a sample. You're not going to talk about random assignment in a sample. And likewise, if you're talking about an experiment, you never want to use the term strata, bias, or random samples, anything like that. These are the terms that are really exclusive to these specific situations. And remember the big difference here with an experiment as opposed to a sample, right? Experiment, you are imposing treatment. You're imposing treatment, right? Whether it's some sort of, maybe it's a medication or some sort of behavior imposing on them, you're saying, you're going to do this, you're going to take this, and then you're looking for results. With a sample, you are not doing that. You are observing. Right? Like if you're watching people run around the track and you're noticing that the short people are running faster than the tall people, You can say, I notice that the shorter people are running faster than the tall people. You cannot come to the conclusion, however, that being short makes you a faster runner. That is not a conclusion you can come to if you're just observing it. However, if you're imposing a treatment, you get these volunteers, right? You get these people who are short, you get these people who are tall, and maybe you account for confounding variables, or maybe you do a completely randomized design so that hopefully all these confounding variables cancel each other out. And then you make them run, right? You say, okay, you guys are going to get the same treatment, you're all going to rest for 3 hours. Maybe you're going to drink some carrot juice, and then you're going to run around the track, and then we're going to time you. That's imposing a treatment. In that case, if you're doing that, you can come to a conclusion that one affects the other. So I'm even going to put down here cause and effect. You can determine that with an experiment. You can't do cause and effect with a sample. However, you can say, I notice. Even if it's something very obvious, you might think like, man, I really should come to this conclusion. You really can't if it's not an experiment. Like say, here's another example. It's a real classic example too. You look around and you're noticing that, I'm noticing that people who smoke tend to cough a lot and they're not as healthy. You can't necessarily jump to the conclusion that, hey, smoking makes you unhealthy and it makes you cough a lot if it's not an experiment. You can observe it. You can say, hey, I noticed this. However, if it's an experiment, you can impose a treatment, right? And maybe that treatment can involve a number of things. Maybe you say, okay, I'm going to take these people, I'm going to block them by, smokers and non-smokers, and then maybe impose a treatment. And this wouldn't be ethical, but you could say, okay, half of you are going to smoke, half of you aren't, and then let's compare the results. You wouldn't want to do that. I'm putting that out there. I'm just implying that you have to impose a treatment to determine cause and effect, whereas you can't do that with a sample. You can just say, I notice. All right, so that basically wraps up our chapter on experimental design. So if you have any questions, you can always reach out to me. But have fun with this. You're going to be putting together some of your own experiments here. You might be looking at situations and have to determine whether it's an experiment or not. And that's important in and of itself, because you want to be able to read things and notice if you can determine cause and effect. Because believe it or not, a lot of times on the news, you might find situations where they try and imply cause and effect, but it's really an observational study. It's just more sensational to, imply cause and effect. And you want to be an educated statistician and not fall for this stuff. All right, guys, best of luck.